All right, so we are starting 2-2, which, if you remember the pattern things we did on the last 2 pages, so you did the car one and the pattern one.
Sure.
That was inductive and deductive reasoning. You just didn't know it. So today we're going to describe what they mean, and then we're going to use them. So the first thing is inductive. Just don't push it too far. And then all right, so inductive reasoning is a conjecture, is an unproven statement that is based on an observation. You're good. So it's based on what we can see. There's no facts known about it at all. We're just looking at something and making a guess, which is a conjecture. You use inductive reasoning when a pattern in specific cases, and then you can write the conjecture for the general. So we're going to come up with an idea for what we think it is for the ones we see, usually a pattern, and then we're going to write what the rule would be for the rest. So to start us off, it says describe the next figure in each pattern. So what would the next one look like, Josh? Do you know?
He's doing it for SRQP.
Oh, well, I'm looking at this one.
Oh.
I was like, what? What would our next figure look like? How many sections should it have?
8.
Okay, and how many are going to be filled in? 1. So do your best to sketch that.
Oh, I smoked that. Perfect. Wait, I aced that.
Share with the group.
So amazing.
Both of the wrong one. Share with the group. Yes, it does. Miss Mimi.
Yeah.
Guess what? I'm going to retry.
What?
Legendary.
All right, then Josh already told us the next one here would be O. We're counting backwards. Not counting, saying the alphabet backwards.
Oh, I know.
What's this next one? Take a second before you hear the answer to try to figure out what it is. I'm going to pause. So to get from 1 to 2, we multiplied by 2. To get from 2 to 3, we multiplied by 3. From 3 to 4, or from 3 to 4, from 6 to 24, we multiplied by 4. So we would take 24 and multiply it by 5, which gave us 120.
What's your favorite number?
16.
Mine's 16. Mine is it because
All right, after that, it says a counterexample. Just keep sliding. To show that a conjecture is true, you have to show it's true for all cases. If we're trying to show that a conjecture is false, we only have to show it once using a counterexample. So this is where proofs are going to come in after our quiz. But in order to say something is true, it has to be true for every single case. If it's false for even one case, even the smallest number possible, it's not going to work. So we always are trying to find a counterexample because it's easier to prove one thing doesn't work than to prove a million do. Okay? So a counterexample is a specific case for which the conjecture is false. Which makes sense. Counter, like a counter argument, is to go against something. So a counterexample would go against what we think the conjecture is.
Oh, I know one.
All right, so the conjecture in the example says, the sum of 2 numbers is always more than the greater number.
I know.
What's an example for a counterexample? Josh?
Like -2 plus like 4 or something.
-2 plus like 4 would give us 2, which is not larger than the greater number. So that would be a counterexample. It doesn't matter what example you find as long as you can find one that's false. Alright, so it says, if a counterexample exists, the conjecture is false. So is our conjecture true that we just made right here? No, because we found a counterexample, so that is not true. Alright, flip to the next page. Alright, so that was inductive reasoning. We were looking for a pattern. We were trying to continue the pattern and then sometimes find one that breaks it. For deductive reasoning, Deductive reasoning uses facts, definitions, accepted properties, and the laws of logic to form a logical argument. This is different from inductive reasoning, which uses specific examples and patterns to form a conjecture. And now we're going to start learning what the laws are. All right, here's the two laws of logic we're going to look at. The law of detachment and the law of syllogism. You need to know what these two things are, so make sure that you know the names of those. The law of detachment says if the hypothesis of a true conditional statement is true, then the conclusion is also true. So if we know that what we're assuming to be true, our hypothesis is true, and we know the whole thing is true, we know that the conclusion had to be true as well. That was our TTT from our truth table. The law of syllogism says if hypothesis P, then conclusion Q. So this is what we're starting with, if P, then Q. If we have if Q, then R, so now we've got a new conclusion, but we're using the same Q, then we can assume P and conclude R. Because this law of syllogism says, if this thing got us here, and that same thing got me here, I'm still going to get to this one. So if the conclusion of the first one and the hypothesis of the next one are true, we're basically skipping that piece and going from our first hypothesis to our conclusion. Okay? We're going to see some examples with words which make it a lot easier. All right. The law of detachment.
0.
If two segments have the same length, then they are congruent. So here's our if P, then Q. Say we know that the segment BC is congruent to the segment XY. What can we say using the law of detachment? So look back at what our law of detachment says. If the hypothesis of a true conditional statement is true, so if two segments have the same length, which we know they do, because it says they're congruent, then the conclusion's also true. Okay, so if we know they're the same length, then we can already tell that they're congruent, even though it tells us they are here. All right, so what statement can be made using the law of detachment? We can say that BC is congruent to XY and they're the same length. Good.
I agree.
So we know both parts of that are true because of the law of detachment. All right, the law of syllogism is my favorite. Bless you. There's a lot of side conversations going on. All right, law of syllogism. It says, if possible, use the law of syllogism to write a new conditional statement that follows the pair of true statements. So this part is key here. We already know they're true. We aren't assuming they're true. We're not deciding if they are. It's telling us they are. All right, it says, if x squared is greater than 25, then x squared is greater than 20. That's one statement. If x is bigger than 5, then x squared is bigger than 25.
Yep.
So what part do they share?
The square.
They share this piece, right? If
Yeah.
the x squared is greater than 25. So the law of syllogism says, if our first conclusion is our next hypothesis, we can skip those and write the other part. So, what would our statement look like then? Keep the same if. So what's our if statement?
X squared is greater than 25.
We're skipping the part they share.
So then if x squared is greater than 5.
Okay, so if x is greater than 5, then we're skipping the part they share. We're assuming that's already true because they share it. What's our conclusion?
Then x squared is greater.
All right, then x squared is greater than 20.
I put out is greater than
You can write it out, that's fine. All right. In the next one. Okay, the side conversations are actually driving me insane. If a polygon is regular, then all of the angles in the interior of the polygon are congruent. What does regular mean?
Oh.
Yes?
Isn't it like open? Or like not closed? Or no, like closed. Or wait, like they're
Straight.
Anybody know this one?
There's no curves.
That's kind of
Spencer?
It's like all straight lines, no curved part or whatever.
Close.
What the heck, dude?
I was
basically
copyright.
said-
I just said that.
It means that all the sides are the same length.
Oh.
So if we have a pentagon, all 5 sides are the same length. One side's not 1 and one side's not 12.
So not what we do that for one.
Alright. So it says, if a polygon is regular, then all angles in the interior of the polygon are congruent. Which should make sense. If all the lines are the same length, then the angles they should all be the same. Our second if statement is, if a polygon is regular, then all its sides are congruent. Is there anything that overlaps here? If a polygon is regular. Alright, but was it the assumption of one and the conclusion of the other?
none.
No.
God dang it.
So we can't apply the law of syllogism here. One of them has to be Q and one of them has to be P in order to skip that piece. We can't skip it if that's our only assumption. So we're going to write not possible for this one. We can't use the law of detachment there. Or sorry, law of syllogism. Yes.
So you're.
Okay. So we're going to use inductive and deductive reasoning here. It said, what conclusion can you make about the product of an even integer and any other integer? So we're going to write a couple down so we can see if we can find a pattern. So, like, let's multiply, let's see, the product of an even integer and any other integer. So, like, let's say 1 and negative 2. What does 1 and negative 2 give us? Negative 2. What does 1 and positive 2 give us?
2.
Okay. Let's see. What about if we did 2 evens, even and odd. Let's keep going for some more. All right, what about 2 times negative 2?
8.
Negative 4.
But are you?
What about 2 times 2?
4.
Okay. What about 3? If we do 3 times negative 2, what do we get? 3 times positive 2. Okay, what are we noticing about our answers we're getting?
It's the same thing. One of them has a negative.
Oh yeah.
Well, what if I gave you 7 times negative 2 and 8 times negative 2?
There's always.
Anything times an even number is even.
Oh, the beginning is positive.
Because we've used odd and even, and we've used negative and positive. What are we realizing? Anytime we use an even integer and what's
Any
happening?
other integer,
It's odd.
It's even.
But we did even times even here.
Oh, the second one is what it is. Right?
What?
Like if the second one's odd, then it's
You times
odd.
anything by 2 and it's even.
What if we used 4?
Times anything by any even number and it will be even.
Is that true?
Yes.
No.
Well, let's write that that's our conjecture. I'm going to write it in math terms because I don't really like words.
Oh, wow. She's right.
Even number times any number equals an even number. All right. That's how I write my things because I don't like words. But if you want to write that all out in words, you're welcome to. So an even number times anything we're saying is going to give us an even number. All right. It says let n and m be any integers. Use deductive reasoning to show that your conjecture is true.
I'm done.
So if we're multiplying something by 2, so we're going to say like 2n. What do we know that 2n is going to be?
Even.
Okay, so if 2n is even, because why?
Anything times an even number is even.
Because 2 times anything is even.
Oh yeah.
Okay, what if we had 2 times n times m? So now we're multiplying 2 by 2 other numbers. Test a couple and see if it still works.
Fill letters with numbers.
Any number. Plug in any numbers you want for n and m and see if it still always gives you a positive.
14.
-1.
Can our conjecture be wrong?
Yeah,
It could be.
Like if you plugged in a negative for the any number, it would come out as odd.
Well, we did that here though.
It's all even.
Yeah, but it says it's equal to an even number.
Even just means it's like a 2, 4, 6. We're not saying positive.
Oh.
We're just saying.
She could like, you guys could just like put it out there like
No.
I think so.
Like, give me 3.
All right, so we can say that 2nm represents
I just write down just so I can see it. I won't-
2n times m. And if we multiply anything by 2, we're getting an even number, right? So then now we've got a bigger even number times any number. Is it still going to work?
Yeah.
All right. So, I don't know how I want to write that. 2nm represents 2n times m. So 2n is a bigger even. So we still have an even number. All right. So that will be good. So this was us using inductive reasoning. We were looking for a pattern. Inductive is finding a pattern. Deductive is making a conclusion about the whole thing. So 2 times anything is going to give us another even number. And even if we multiply it by an odd number here, we're still multiplying by 2 at some point, and we'll be able to divide by 2 in the end. So anything that's even is divisible by 2, which is true. All right. Comparing inductive and deductive reasoning. Decide whether inductive reasoning was used or deductive reasoning was used to get to each conclusion. So read these with your table and see if they looked for a pattern or if they used prior knowledge.
Okay.
Is inductive because of the pattern of kicking the ball. All right, B says all reptiles are cold-blooded. Parrots are not cold-blooded.
Wait.
Dave's pet parrot is not a reptile.
That's deductive?
Inductive or deductive? Did we look for a pattern or did we go off prior knowledge, Liam?
It's prior knowledge because it says all reptiles are cold-blooded.
All right, that's not an experiment you can look for. Like you can't just test a bunch of animals and be like cold-blooded, warm-blooded, cold-blooded, warm-blooded.
you could.
You could, but you'd probably kill them.
Justice for animals.
So this would be deductive reasoning
Deductive reasoning.
Studying, get hit.
because they use the law of logic there as well.
Okay, that explains it.
All right, that's it for our notes.